in the morning, so it's still fine. So let's continue with the mechanical properties of polymers. And we finished by looking at this ASB chart, essentially, where we can see that polymers generally show a relatively mediocre cost compared to different types of materials, such as metals and alloys or ceramics, but significantly lower Young's modulus. And the same applies, of course, for the strength of polymers compared to metals, let's say, where metals are sitting here in terms of their Young's modulus. So what's the advantage? Why then should we be using polymers instead of metals? And of course, one justification is, of course, they're lightweight. Okay, several polymers are much lighter in terms of their weight compared to metals. So one justification is that of course there are metals that are lightweight, okay, such as titanium or aluminum, but generally polymers show much lower weight compared to metals. However, in terms of their mechanical properties, let's have a look at this stress strain curve for steel versus polycarbonate. Okay, polycarbonate is an amorphous thermoplastic. So what we can see from this graph, we can see, of course, very obvious that the modulus of steel, and the modulus is taken from the slope of the initial part of the stress strain curve. This is the modulus of the steel. This is the modulus of polycarbonate. It's obvious that the modulus of the steel is much higher than the modulus of the polycarbonate. Okay, and also you can see that the Young's modulus of steel, I don't know, can be seen around here. Well, the Young's modulus of polycarbonate can be seen here, let's say. So the Young's modulus of steel is also much higher than the Young's modulus of polycarbonate. However, even though the mechanical properties of steel are much better than the mechanical properties of polycarbonate, the advantage that polycarbonate has is that it has much larger elastic deformation. Okay, you can see that the area before the yield point is much higher in the case of polycarbonate compared to steel, which is, I don't know if I can even plot it. It's only, let's say, this region here. Okay, so from that graph we know that the absorbed energy before plastic deformation is much higher than polycarbonate for polycarbonate than steel. Okay, okay. Plastic deformation means that we have a permanent shape change. Okay, here when we move in this elastic region, we don't have no permanent deformation. Okay, the same applies for ceramics as well. Okay, and not only same, but ceramics, we said that they can only elongate up to 1 to 2%. So they're much more brittle than steels, and they do not show any amount of plastic deformation. Okay, they just used extensively. We already spoke about the excellent impact. Do you remember why we said that? Because of secondary glass transitions, which enable dissociation or absorbing any significant impact energy. Okay. Yeah, this is I forgot about that. This is the example where, of course, we have a certain amount of deformation for polycarbonate, but the absorbed energy is much higher on polycarbonate than steel. Okay, and I'm pretty sure you've seen videos where essentially when you have a bump like that in your car and you use heat, I think that's what they're trying to show, that they're heating the material in order to soften it up, and then they bump it out essentially in order to fix this bump by making the change move much easier and then shaping the material. Of course, it's not this situation is not perfect, but you can fix it much easier compared to a metal. Okay. Now, how do we test the mechanical properties of polymers? We have been talking about obtaining different types of properties through stress strain curves, but how do we generate these stress strain curves? Well, it's relatively easy. In order to test the mechanical properties of our materials, we create these shapes that are called dumbbells or dog bones that look like that. Okay, and that's how a mechanical testing or tensile testing specimen looks. Or sample, okay, and some people call them dumbbells. It's with 1B. Anyway, 1 or 2, or a dog bone, because I'm not sure if you have seen it in cartoons. They represent dog bones like that. Okay, it's fine. Now, once we create this characteristic shape of polymers, okay, usually we do that by stamping them with knives. Okay, we have a continuous sheet of polymer, let's say, that looks like that, and we have a press which has a knife essentially, and we're stamping the knife on top of it, and we create the specimen that looks like that. Okay, so from a sheet of polymer, we obtain multiple tensile testing samples. Okay, so once we create this shape of materials, we place it onto the tensile testing machine. Okay. The reason why we have this particular shape is because we want to increase the area that is gripped from the machine. So we want these areas here to be gripped from the machine. So these are the grips, okay? So this is the area that is gripped from the machine, and that is what you cannot see here, okay? This is under here, okay? And the upper part of the tensile testing machine is the moving grip. And the bottom part is the stable grip. Okay? Usually, okay? Because here, this machine shows the opposite, okay? In the vast majority of cases, though, the upper grip is the one that is moving, and the bottom is stable, okay? Because that one, the one represented here, doesn't make much sense, because you would need to load your sample very high if you have let's say an elastomer that elongates a lot. Okay, it's easier to fix it in a stable position at a normal height and then let the material elongate a lot. Anyway, one grip will be moving and the other will be stable. In this case, they're moving the bottom one. Okay. The test at constant speed. And for different types of materials, we have standardized tests. Why is that? It's because we want to compare different types of materials with the same testing conditions, okay? And that is why there are conditions that are by ISO and guidelines for the measurement of different companies. So for elastomers, we generally have speeds up to 500 millimeters per minute. And that is not relatively, it's a very fast condition to test because elastomers can elongate a lot. Imagine if we're pulling an elastomer very slowly, we're not only allowing the sample to elongate a lot, so the measurement will take a lot of time, but also because we're moving very slow, we're allowing the chains to relax at each situation, okay, at each pulling condition. And by that, we allow even further elongation than normal. So for elastomers, we do it relatively fast. For thermoplastics, it's around 50 millimeters per minute. And also for thermosets, it's relatively slow because we want to have a good resolution of materials that are brittle, okay? So we want to obtain as much information as we can. So for thermosets, we have 5 to 10 millimeters per minute, okay? These are the speeds of testing generally, okay? Now, this is how a normal testing setup looks, okay? This is a tensile testing equipment. Of course, there are different types of testing, okay? It's not only tensile testing in order to obtain mechanical properties. We can have also compressive testing, where you can obtain the compressive properties of materials by 3 or 4-point bending tests. In this case, we have an upper part of the machine that looks like that, and a bottom part that looks like that. Okay, and you position your sample here, let's say. You stabilize it, and then you move the upper part towards the lower part, and you measure compression characteristics, okay? So you put continuous force in order to allow the sample to break under compressive force, okay? Three-point bending. Also, as I told you, we can have impact testing, where impact is another type of mechanical property. Impact testing is much more straightforward. It's interesting, but more straightforward, more simple. In impact, you have a grip like that, okay? You fix your sample here, which looks like that, and then you have a pendulum that comes and hits the sample. You have a pendulum or a weight or something. So this is a pendulum. That is for impact, okay? And you measure how much energy is absorbed from the sample. Anyway, it's not that important. Now let's have a look at the normal tensile testing equipment. You can see these are the grips. Okay, this is what I told you. It is very important to ensure that our sample does not move when we're pulling along the direction, okay? This is the pulling direction, as you can see. So we need to fix the sample very well in here. The sample looks like that in here, okay? We need to fix it very well. And we also need to measure very accurately how much elongation takes place in this region here. That is why, in this case, we use a machine, not machine, a setup that's called extensometer. Okay, and extensometer gives us gives us a very, very accurate amount of extension for our samples, okay? Gives us very significant information about elongation. As you can realize, final thing, the grips are interchangeable. Huh? So within this machine, we can have a setup like that. or a setup with a 4-point bending and so on. So grips are commonly interchangeable. What else? I think that's pretty much it for tensile testing. Yeah, as you can see, there can be different shapes and different sizes of the samples for tensile testing. These are determined by ASTM test methods, as I told you, or ISO. These are both ASTM and ISO. These are committees for scientific standards. Okay, as I told you, we need to compare similar things under similar conditions, and that is why these test methods have been proposed by these companies. What is very important here in the sample size, what is very important is this length here. Okay, this length here is called the gauge length. And essentially, it is the length of the material that elongates, and we obtain the mechanical properties of our polymer from that, okay? And that is why the gauge length is very, very important to be measured accurately before we start pulling, okay? So the gauge length needs to be accurately determined for test. Okay, that is all we have to say for tensile testing. Any other questions for tensile testing, please let me know. Now, we said that the mechanical properties of polymers are very broad, okay, because the family of polymers is very broad, okay. So you can see that we have materials that there are thermoplastics that can show elongation up to 600%. Well, we have some very high engineering polymers that can elongate only up to 6% or 4% or 10%, okay? So the range of elongation is very wide. The tensile modulus, of course, it's also very wide. We can have materials that range. Let me see. We don't have any elastomers here, but even we have thermoplastics that can have a Young's modulus in the order of 300 megapascals. This is very soft, okay? This is for low density polyethylene, such as the one that's used for plastic bags, okay? And you can see that polyethylene, just two grades of polyethylene, low density, high density, you can see how much differences they have in terms of their tensile strength. The tensile strength is double for high density. Of course, it's more than double for ultra high density. Well, the tensile module is 4 times higher. Is four times higher for high density polyethylene. So you can realize by controlling the molecular weight of our polymer, how much we can control the tensile properties of our materials. I think that high density polyethylene should have slightly lower elongation, but okay, I'll just believe the table for now. Now, of course, there are types of tricks we can do in order to control the mechanical properties. Does anyone have any idea what can we do in order to, let's say, modulate? How to modulate? The mechanical properties. Any ideas? What can we do in order to modulate the mechanical properties of a polymer? There are obviously a very large number of strategies. We have discussed several of them. I have a couple of ideas. Anyone else? Yes, very well. Yeah, chemical modification is indeed a method, but it can be a bit challenging compared to other more simple methods. Let me check the materials group. Pillars. What are you writing with faith? Division of labor, excellent leadership. What are all these? Okay. Yeah, control the working temperatures. Let me think of that. Control the working temperatures. Not sure about that. But the majority of suggestions are really nice. So we can modulate the mechanical properties of polymers. Firstly, we said one method is blending with other polymers. Also, we can do a copolymerization, fabrication of a copolymer. We can add substances such as, let's say, plasticizers. Plasticizers are generally known to make the material much softer, okay? So we can add. We can add fillers. Fillers are having mechanical properties that are much better than polymers. For example, we discussed about graphene, which has a modulus of 1 terapascal and 130 gigapascal. Compared to all these, you can see how much difference adding graphene in there can make. So addition of fillers. Obviously, control of the molecular weight. Okay, these are some of the very easy and straightforward techniques that we can use in order to modulate the mechanical properties of polymers and essentially create what we call material by design, okay? So we decide before we even fabricate our material the properties that we want our material to have, okay? And then based on the properties that we want, we fabricate the specific material by following specific strategies, okay? Now, let's have a look at another RB chart. This RB chart essentially, I only used it in order to show you that even though the toughness of polymers is quite broad, okay, you can see that we have polymers that are both that are highly ductile, okay. Ductile means they're able to elongate. So the toughness of polymers is relatively good compared to other types of materials. The toughness is a combination of strength and elongation, okay? Unfortunately, the strength of the polymers is not great, and that limits a bit their application. You can see that the range of strength of polymers is relatively narrow. Okay, you can see that metals have much higher strength distribution, and also some foams as well. Okay. So the strength and stiffness of polymers are fairly similar, but the strain at break and hence toughness can vary widely. Now, I introduced this slide here, even though it can seem a bit cut off from what we have discussing, in order to introduce you to the concept of the glassy polymers, which are the most difficult to understand. And so far, ourselves, scientists, we still have not a very clear idea what's happening during the stress strain behavior of glassy polymers, because these materials so complex molecular structure in terms of their completely amorphous state. Okay, so glassy polymers are amorphous, as we said. So because of their completely entangled network of chains here, it's very, very difficult to predict and very clearly understand that the different stages of a stress strain curve. Okay, we will analyze glassy polymers as much as we can later in this section. Okay, most probably either later today or on Monday. Okay. Anyway, glassy polymers can show two different behaviors. Okay, so they can show a brittle behavior, which is very straightforward. Okay, the brittle behavior for a stress strain curve, it looks like that. So the material doesn't have enough time to have any chain arrangement along the chain direction, because crosslinks are strong and so on, and entanglements are so strong, and it breaks very fast. Okay, so this is a brittle material. However, we have glassy polymers that can elongate slightly longer. Okay, so we can say that they're slightly ductile. So the materials with the slightly ductile glassy polymers, so a behavior that looks like that. Okay, it is similar to what we saw yesterday for semi-crystalline polymers. Now, I should say that when we examine a polymer, initially we're not sure if it will show a brittle or a ductile behavior. So we need to test it in order to observe it. So brittle glassy polymers include polystyrene, PS, or polycarbonate. And ductile, I'm not sure what are the teaching assistants are saying. I get some text messages from them. Give me a second. Okay. Yes, I can wait a bit. Sorry, guys. I've been notified for a technical problem in 204. Sorry, guys. Let's wait for the other class as well to get connected. Okay. We have the materials group that's completely disconnected from the meeting. Okay, guys, take a 10-minute break. Yeah, I see that 204 is connected now, but take a 10-minute break now, and we will resume with normal progression of the course. Okay? I'll see you in 10 minutes. If the materials group hasn't heard, please take a 10-minute break now, as it's time for a break, and we will resume our normal status of the course after the break, okay? So see you in 10 minutes. Can the people from the polymer group let me know if you can hear me, because I can see 204, which is the materials group. Okay, I cannot see you, but it's fine. Okay, so let's resume. I was telling you before we stopped, the connection dropped. Essentially, I was telling you of the complex behavior of glassy polymers. Okay, and in terms of glassy polymers, it is so far unknown how the stress strain behaviors varies from one polymer to another. Okay, and generally how it depends on specific chemical structures of the monomers and intermolecular interactions in amorphous materials. Okay, and in terms of glassy polymers, I was saying that they can show two types of behaviors. They can be brittle or slightly ductile. Okay, by saying brittle, they fracture very, very fast at very low strains. By saying slightly ductile, I mean that they can elongate, of course, not at all in the context of a semi-crystalline material or, of course, an elastomer, but they can still elongate by a process that is called necking. And we will see that more. The glassy polymers, the brittle polymers deform with a process that is called crazing. We will see a lot of information about the crazing and necking in a bit, okay? Yeah, this is how a brittle stress strain curve looks. We do not have any plastic deformation because after the elastic region, the polymer fractures, okay? The bonds and the crosslinks are very strong, and the carbon-carbon bonds break immediately after the elastic region. Now, some characteristic examples of brittle glassy polymers are polystyrene and polycarbonate, okay? While ductile amorphous polymers, two examples that I can give you is polycarbonate and polyethylene terephthalate. This is, we said that polyethylene terephthalate is used extensively in bottling applications, because it shows an exceptional permeability. Okay, it does not allow gases to escape when they're in the bottle. Okay. Now, as I told you, the stress strain behavior of glassy polymers is a bit complex, and yeah, I told you 208 has a problem. Okay, I'm waiting. Sorry, guys, nothing I can do. The TAs are starting to wait. I'm not sure if I will ever finish with this slide. It's been like 20 minutes we're stuck on that. It's not that important at this stage, this slide. Anyway, we wait. Mhm. I got a couple of questions for the coursework. I'll answer these once we finish. Can the TA from 208 let me know if you can hear me? I cannot see the camera from 208, but I see that it's connected. Can you hear me? Okay, I can see the camera as well. So let's continue after these disruptions. Let's try to escape this slide. Essentially, I was telling you that amorphous polymers have the most complex types of deformation, because we generally do not understand how in amorphous or glassy polymers the stress strain behavior varies from one polymer to another. Okay, because it depends on specific chemical structures of the monomers and intermolecular interactions between happening here with the change of the amorphous polymers is, of course, in the elastic region here, the amorphous chains are starting to slightly disentangle and stretch, okay, and they form these um, oriented chains. But after the yield, and that is something that is not seen in this stage here, we have stretching and sliding, okay? So once these crystalline regions are formed, they immediately break, okay, into lower pieces. That's why we have this part here where we have strain softening. Okay, and then once the pieces, the crystalline regions that have been formed due to stretching and sliding start essentially stabilizing, then they start orienting again along the stretching direction, and we have increased stress by a process that is called strain hardening. Okay, this process though takes place only in those slightly ductile glassy polymers, okay, that elongate by necking. We will see, I told you in a bit, how necking takes place. Let's move on because we've lost quite a bit of time. As you can realize, and as I told you, there is a significant effect of the strain on the ultimate properties of the mechanical properties of polymers, but also there's obviously an effect of the temperature, okay? And it's easy to understand why temperature can affect the mechanical properties of the polymers, because the chains have much more energy in order to move around, okay? And because they have much more energy in order to move around, that helps them disentangle, okay? So with increasing temperature, okay, increasing temperature or decreasing speed, we have disentanglement. Disentanglement or relaxation of chains, essentially, that allows them to orient towards a certain direction. But generally, disentanglement takes place much easier. At low temperatures, we have brittle fracture. Can anyone tell me why at low temperatures we generally observe brittle fracture or brittle failure? Why at very low temperatures we generally observe brittle failure? Yes, what Hans suggests is correct. The temperature is lower than the glass transition temperature. And what did we say that happens to the change where the temperature is lower than the glass transition temperature? Juan and Daniel already answered that in the polymers group. They said that the chains are frozen, okay? The chains are frozen, the chains do not move as easy, okay? And polymer is embrittled because the chains do not move towards the direction of strain. Now, of course, with increasing temperature, of course, we said that we give enough thermal energy along with the strain that we're applying in order to disentangle the chains and elongate them. That is why we observe plastic deformation with increasing temperature. You can see that as higher temperatures as we apply, we decrease modulus and strength, but we increase the energy to break, okay? The energy to break, we said it is the toughness. So the area here, of course, as you can realize, it's much higher than the area at lower temperatures, okay? Of course, there is a temperature at which we have a transition from brittle to ductile transition temperature. And that is very specified. It's tough Vita, it's called, and it is named brittle to ductile okay? So this temperature is observed when the temperature is increased and the behavior of the polymeric material changes from brittle, okay, to ductile in deformation and ultimate fracture. And yeah, that is essentially what we were saying earlier. We can see that with increasing temperature or decreasing strain rate, we have strain rate can be given by this equation as well, okay? This expression is the derivative of strain over time. Okay, so increasing the temperature decreases the modulus, decreases the tensile strength, and increases the strain at break. Okay, and here you can see that here we have a brittle deformation, here we have a ductile deformation, so that tells us that tough Vita, okay, the brittle ductile transition temperature is between 40 and 60 Celsius degrees. Okay, this is for polymethyl methacrylate. Now let's have a look at the stress-strain behavior of different families of materials, such as elastomers, thermoplastics, and brittle polymers. Usually, we use a thermoset example. Okay. So let's go to the notes section. Let me continue here. Yeah. Today, the date is the 18th. And let's have a look at the deformation of elastomers. Okay. We already spoke about elastomers, so I'll try to refresh your memory essentially. Can anyone give me what are the requirements in order to say that a material is elastomeric or an elastomer? Which are, let's say, the two most characteristic features of an elastomer. While you're writing, I'll start preparing the stress strain curve. Yes, indeed, the elastomers have low amount of crosslinks. They generally can have high strains at break, higher than 300% indeed, and a very low amount of crystallinity, okay? Or almost zero crystallinity. So elastomers are lightly cross-linked materials with a low amount of crystallinity. Okay? We said that elastomers show a stress strain behavior that looks like that. Something like that, let's say. And generally, okay, the deformation in this region is fully reversible. Because of the phenomenon that we discussed, it's called entropic spring effect. Okay, we said that when we're stretching a, we reduce the number of conformations that the chains can take. We orient the chain along a certain direction, and that reduces its entropy. However, the system thermodynamically strives for maximum entropy, and that is why in elastomeric materials, the system is able to retract its original shape without significant problems, okay? Because of the entropic spring effect. We said that for elastomers, we obtained the moduli at different regions, such as 50%, 100%, or 300%, let's say. You realize what we said that, okay? Because elastomers can elongate a lot, so the elastic regions of elastomer is very wide, okay? So when we want to compare elastomers, we need to know at which essentially strain we obtain the linear fit for the modulus. So if we take it, let's say, for 100% strain, perform the linear fit like that, and we take slope here in order to obtain a modulus at 100% strain. That's how it's called. Okay. Finally, something interesting that we said about the elastomers is that at a certain point they have a deviation from theory. This is theory, and this is experiment. At high strains, the chains become aligned, okay? And because they become aligned, we have strain-induced crystallization, okay? So we have a deviation from theory due to chain stretching and strain-induced crystallization. And because we form those crystallites onto the structure of the elastomers, the crystallites deviate or slow down crack growth. Generally, the fracture of elastomers takes place because of the breaking of the carbon-carbon bonds in the main chain, but also another phenomenon that is common in elastomers. We didn't comment on that when we were discussing elastomers. Is also we have a void formation, because in elastomers we generally use a lot of additives within the structure of elastomers in order to cure them, in order to reinforce them, and so on. And the void formation can take place at higher strains, and with further elongation, voids grow, and that leads to fracture as well. Okay, so this is how elastomers essentially are deformed. Let's have a go at thermosets. Can anyone give me a couple of characteristics for thermosets? How would what would you expect to see if you characterize a thermoset, let's say? What is their structure? How is their network, and so on? Yes, indeed, they are brittle. They're very highly cross-linked, very well. They do not display a melting point, very well. What about the structure? Are they crystalline, non-crystalline? So thermosets have a glass transition temperature. They don't have a melting point. So thermosets are amorphous materials, glassy materials, amorphous polymers, let's say. The network is highly cross-linked. That is chemical cross-linking. Okay. We generally need heat in order to induce cross-linking, so I'll mention that as well. No, you don't always need to induce heat to induce cross-linking. I'll refrain to that. But the deformations in thermosets are non-reversible. Yes, indeed, and a 3D cross-linked network, of course. 3D cross-linked. And because we say that deformations are not reversible, and that is why I mentioned that we cannot recycle thermosets. Okay, once the thermosets fail, we cannot do anything about that. While in the case of a semi-crystalline material, such as a thermoplastic, semi-crystalline thermoplastic, such as polypropylene or polyethylene, if a polypropylene material fails, again, we can chop it down and reprocess it without problem. So thermosets generally show this type of behavior, either very highly brittle behavior, or they can show a behavior where we have a little plastic deformation, but only a little, okay? So, okay, just a second. My computer thinks it hasn't. It's still night, okay. So here for curve number 1, we have a thermostats with high TG and highly cross-linked density, high cross-linked density. That makes them hard because they have very high stiffness and strength. Okay, hard means high stiffness and strength. Okay, and brittle. And curve number 2, they can show a slightly lower cross-link density. They are still considered brittle, okay? The reason why thermostats do not display any plastic deformation is because of the high cross-linking. The chains cannot align themselves in the tensile direction, okay? So there's no plastic deformation and no strain hardening. Because of high cross-link density. Chains cannot in the direction of strain. Okay. Generally, their modulus is higher than 3 gigapascals. And as I told you, they show very little. Sometimes they show very little plastic deformation, such as in this case, and they always show a low strain at break. Okay. And finally, the most complex behavior is seen by thermoplastics, as we saw the other day. We saw semi-crystalline thermoplastics the other day. Thermoplastics can be also amorphous and semi-crystalline. If we take the most complex case here, where we have extension by necking for stress versus strain curve, we can have behavior that looks like that, or behavior that looks like that. Okay. Here we have the yield points, or here we have, let's say, the elongation at yield, and here the yield point is the onset of necking. Okay. In this region here, where we have a drop, let's say, of the strain, this material, the process that takes place here is called strain softening, where we have the process that takes place during strain softening includes uncoiling of the chains and chain slippage. We break the entanglements. And we have also change slippage. We said that any crystalline regions that are formed or pre-exist, what happens is that they can slide against each other, okay? So sometimes they're still connected, but the crystalline regions break down, and that is why we have a drop of the strength of the polymer in this region. But still, after this region, you can see that there is further increase of the strain, of the stress and the strain. And that takes place because we still, even though these chains have broken down, they still manage to extend along the tensile direction. So in this case, we have strain hardening. So we have increase stress. That is, the increase of stress gives an increase in the load-bearing capability. Okay, the material can bear much higher loads. Increase of and we have alignment of chains in the tensile direction. Okay, so these are the three main families of polymers: elastomers, thermosets, thermoplastics. That is how we expect them to essentially deform or form the strain curves. Yeah, so these. Yeah, we also have the systems where they are highly oriented, such as fibers. The fiber fabrication takes place by drawing, okay? So by aligning the chains in the drawing direction, drawing is pulling, okay? And we're stretching the polymer prior using, okay? Essentially stretching. Drawing can take place at elevated temperatures or at room temperature, okay? As you would expect, at elevated temperatures, it's easier to orient the chains because the chains already have a certain amount of thermal energy in order to move around. And because they can move around, they are easier to elevate. But also this can take place in room temperature, but we cannot generally achieve high draw ratios at cold drawing, that is at room temperature, because the material is much more prone to fracture. So you can see here we have aligned chains. We have an increase in the modulus and the strength in the drawing direction. Of course, the material becomes brittle, so it fails at low strains, okay? But we increase so much the modulus and the strength of this material that is certainly worth the effort, because we said that in the pulling direction, okay, that is the direction where the chains are oriented, the modulus can be in the order of 10 to the 11 pascals, that is the 100 pascals. While of course in the when we're pulling in the direction perpendicular to the orientation of the chains, the situation is not as good, because as you can realize, we don't have reinforcement towards this direction. So in this case, the modulus is in the order of 10 to the 9 pascals, or a couple of gigapascals. Okay, and with that, we'll finish for today. We will resume on Monday with the rest of the mechanical properties. I was hoping we could say a few more things today, but technical problems did not allow us. Anyway, we will make up for the lost time on Monday. Don't worry about that. Enjoy your weekend. Any questions about your coursework or the course in general, please feel free to shoot me. And have a good weekend. Get some rest and see you Monday. Bye, guys.